All right, so in the second part of how electricity and magnetism are related, we're looking at Faraday's law, right? Which is saying a change in magnetic fields strength through this circle, through this area, will create a voltage, which is, and remember, a voltage is the same thing as saying an electric field lines times the length, right? That's voltage. So this is voltage, right? Meaning this is the voltage that gets induced. Now, what is happening and what does Faraday's law mean? But before I get to that, let's look at down here. This is Ampere's law. So this is saying that a magnetic field around this wire will be induced if there is current in the wire, right? So there's, you see how there's two parts to this equation. So here, the current that gets that is flowing through this region, right? This curling magnetic field line, there's current in here moving this way. Okay, it will produce magnetic field lines curling around this current carrying wire. Now, using the right-hand rule, current's going this way, so magnetic field lines will flow in front of it, right? Now, what does this part mean? So when this is a capacitor plate, so when charges start to accumulate on this capacitor plate, electric field lines start to appear, right? And they build up and build up and build up. That's what this is saying, is that there will be magnetic field lines that start getting created in here around a changing electric field line. Okay, so that's the thing. There has to be electric field lines that are changing, right? Getting stronger or weaker. Okay, so if there's electric field lines shooting across this and there's the same strength at all times, you're not going to have a magnetic field around it. A magnetic field in between these capacitor plates only appears when the electric field lines start to increase. Okay, so we'll talk more about Ampere's law when we get past Faraday's law. Okay, so Faraday's law, I drew a current carrying wire right here. Now, let's just look at what's going on. What it's saying is the electric field times each point along this, this circle, right, this circular wire. If you multiply the electric field strength at this point times this small length, and you do that for every little length and you add them up, what you get is the total electric field line strength times the length of this entire wire. That is equal to the negative change in magnetic flux, which is also the same as saying the negative change in the magnetic field strength times this area that it's cutting through. Okay, so what I'm just going to draw and see, you can see what's going on. Here is a magnetic field line. Here's three magnetic field lines, right, coming through this wire. Now, nothing's changing. There's magnetic field lines and they stay the same strength. Now, what happens if I add, right, 4 little magnetic field lines, right? We add 4 more. So the magnetic field strength has changed from these 3 to all of these. What happens? Well, there's going to be a voltage that gets induced in this wire to do what? To create magnetic field lines in the opposite direction that directly cancel out these magnetic field lines so that this magnetic field strength stays the same as it started. So that's something that the universe does. When something's changing like this, the universe does something to create opposing magnetic field lines. And so in order to create these opposing magnetic field lines, the curl of the electric field and the voltage would be going clockwise, right? So it would be going this way. It'd be moving around this way, right? To create magnetic field lines downwards. So that would be clockwise. That would be clockwise electric field lines. And so what that is saying is that the magnetic field increased. So looking at this equation, we can say negative B final minus B initial times area over time equals electric field times length. Okay? So the final field, right? What this is saying is the final field was stronger than the original field. So the electric field will be going in the opposite direction. So if you divide both sides by -1, right, this one will go away, you would see that B final minus B initial, B final is bigger than B initial, so it's positive. This would be negative. The electric field is moving clockwise, which is a negative electric field direction. And that is the same as saying a negative voltage was created, right? So a negative voltage gets created to produce a negative electric field strength, which induces a current if there is a current carrying wire that this is moving through. Now, let's say it's just moving through empty space where there's no charges or anything like that. What's going to happen, right? We start off with 3 magnetic field lines. Okay, and let's say that the magnetic field strength gets stronger, just like it did. That is going to create electric field lines in this direction, which creates a voltage that is clockwise, which then creates the induced magnetic field lines to take it back to its original state, which was this, right? It wants to get back to this. It tries to maintain this, right? That's what's happening here. So electric field lines go this way. Now notice there's no charges able to move, so there wouldn't be a current, yet there's still voltage that appears in space. So that's very important, that the changing magnetic field creates a changing, right, an electric field that gets stronger and stronger. As more magnetic field lines go this way, an electric field gets stronger and stronger this way to produce more magnetic field lines in the opposite way. In response, right? So part 1 is we have magnetic field lines starting with. Part 2 is these new magnetic field lines come into existence. So there's just more magnetism there. Part 3 is the electric field gets induced. Part 4 is Lenz's law, which says that a magnetic field will appear that opposes the changing magnetic field to start with. Okay, so Faraday's law is concerned with the voltage, the electric field that appears when there's a change in this magnetic field lines. So 1, 2, and 3 are essentially Faraday's law, and 4 is Lenz's law. Okay, that's important because that's how electromagnetic waves get, how they propagate through space. And you can see here, right? Remember Gauss's law, where it was magnetic flux equals B dot dA, which equals 0 when it's a closed, when it is a closed 3D, when it's a closed 2D surface on a 3D object, right? Like a ball, like a sphere, right? A sphere is a 3D object. Well, the surface area, when you integrate all the magnetic field times each area on that ball, the total flux will be 0 because magnetic field lines come into the ball and will go out of the ball equally. Okay, so this is relating Faraday's law with Gauss's law for magnetism. And then down here, this is relating Ampere's law with Gauss's law for electric fields. Okay, hopefully that makes sense. Now let's get down to this part. Okay, so integrating each point length along this magnetic field line, and if you multiply each strength of magnetic field line at each point, you get this. It's the total magnetic field strength all the way around times the length of this circle. That will be equal to mu sub naught times the current that is enclosed by this magnetic field lines around it. So the current that is enclosed by is just all this current that's moving this way. So this part only relates creates a magnetic field for the current carrying wire. Now, what is this part? That is when the charge starts to build up on a capacitor plate and electric field lines start to grow, right? As more and more charges get on here, electric field lines start to grow, right? And those electric field lines, as they get stronger or weaker, magnetic field lines start to appear. Okay, now if the electric field lines are staying the same strength, that magnetic field doesn't appear. There has to be a change in this electric field line strength. Okay, so let's look at the first part. Current is moving to the right. Positive charges. Using the right-hand rule, we can say that the magnetic field line is this way, right? And why is this happening is because there's an electric field moving through it, right? And charge is moving through a current carrying wire, so we know using the right hand rule which way this magnetic field line will go. Now, what's happening? Let's say charges start building up here. Start building up. So then these electric field lines in between the capacitor plate where the positives repel the other positives away over here, the current starts flowing away, and then we're left with negatives, right? Then we have electric field lines going from positive to negative, and they get stronger and stronger. And so what happens here? The current starts getting weaker and weaker, and then now the electric field lines start to appear, and now we start to have magnetic field lines appear in here, and then this one diminishes and gets smaller, right? It would go smaller and smaller as this one gets bigger and bigger. Okay? All right, so you can see that this part right here is for the actual current carrying wire, and this part is for the what's called displacement current or imaginary current. So that is when the electric field lines start to appear. It creates a magnetic field as if current is actually traveling across this capacitor plate. So this is relating the magnetic field to a changing electric field, okay? And this one up here is relating the electric field to a changing magnetic field. So what that is meaning is when we see a wave, an electromagnetic wave, that's how light travels. It's a wave that propagates. So as this part here gets stronger, right, at each point, so it's getting stronger, this also does the same thing with it.